In 1900, there was a scientist named Max Planck who basically wanted to know, why do hot objects glow? And we see the picture on the screen here, and we all look at that and say, well, that piece of metal, that's hot because it's glowing. But why do hot objects actually glow? Well, Planck concluded that this is energy that's being released in small specific amounts called quanta, like a quantity. And it's a minimum amount of energy change. So essentially the metal takes that heat energy and converts it and releases it as heat energy and light energy in these small packets of energy called quanta. And so a few years later, Albert Einstein, whom we all know, observed something called the photoelectric effect, where when a light was shined onto a piece of metal at a certain wavelength, it emitted a stream of electrons. And he was able to measure the voltage of those electrons that came off of it. And so these two things combined, or these two studies combined, put together a phenomenon called wave-particle duality. And they concluded that light has properties of both waves and of particles, kind of like a boat existing on the waves of an ocean. And this particle of light, Einstein called a photon. And so this photon was what Max Planck was observing when he observed this small quantity, this quanta of energy being released from hot objects. So whenever we see light, we've talked about it earlier, traveling as a wave, but it also exists as a packet of energy, as a photon, a particle. And so because of that, we can use an equation that we see here in order to calculate the energy of a photon in joules. And we concluded that the energy is equal to a constant named Planck's constant times the frequency of that wave. Planck's constant is 6.626 times 10 to the minus 34th joule seconds. Don't worry about the units. If you do the math right, the units will cancel themselves out, and you'll find energy in terms of joules. So let's look real quick how we would use this equation. We want to find the energy of a red photon with a frequency of 4.57 times 10 to the 14th hertz. So let's look to see what we're given. We're trying to find energy. Our frequency is given to us right there in hertz. Shouldn't have to change that. And the h, that's that Planck's constant. That's always going to be 6.6262 times 10 to the minus 34th. So simply, we are going to multiply those values together. And please remember, when you're putting these in your calculator, to use that exponential button. Put them all in there together, and you should get 3.03 times 10 to the negative 19th joules. The amount of joules that you're going to get are going to be a very small number, because each photon obviously contains a very small amount of energy. If we look at a more practical example, find the energy of a wave coming from WMEE, which has a wavelength of a frequency of 97.3 megahertz. So in this case, we need to convert that to hertz. We need to divide those by 1,000,000 hertz to get 9.73 times 10 to the 7th hertz. And we're simply, again, going to multiply this by Planck's constant. So we're going to line those up. Planck's constant times the frequency of WMEE. And we're going to end up with an energy of 6.44 times 10 to the minus 26th joules. Now in the problem before, red light had an energy of 10 to the minus 19th joules. The wavelength of this radio wave, or the energy of this radio wave, has an energy of 10 to the negative 26th joules. That's about 10 million times less the energy than the energy of a red photon. So we would say the energy of a red photon is about 10 million times the amount of energy as that of a radio wave. So we use these energies to compare two waves. We're not necessarily concerned with the individual values of energy, but comparing those. And if we would calculate the energy of an X-ray or a gamma ray, we would find that they are much more energetic than this radio wave. And this leads us then into Bohr's model of the atom. He was taking this information with the electron and noticed that when we looked at red light through when we look at white light through a prism, it breaks it up into all different colors of the spectrum, Roy G. Biv. And we've all seen that anytime rainbows develop, the raindrops are used as prisms. But the one thing Bohr noticed is he took a spectrum of just hydrogen, took some hydrogen atoms, put them in a glass tube, and sent some voltage through them so they'd light up, looked at them through a spectroscope just like we did in class, and noticed that we don't see all the colors of the spectrum, but we see an individual line spectrum. And so he had to draw some conclusions from this. And what he concluded is that electrons exist in two states in the atom. They exist in the ground state and in the excited state. And most of the time they like to be in the ground state. The only way they can get to the excited state is if we input some energy, if we input some electrical energy or heat energy. And as they move up to the ground state and fall back down, they release that energy in terms of a photon. And so if we're only seeing specific wavelengths of light, then there must only be specific energy levels that an electron can exist on. And so that's how he came up with his orbital model of the atom, stating that electrons can only exist in specific orbits with specific amounts of energy, much like the planets can only be in specific orbits around the sun. Or we look at them like the rungs of a ladder. You can only step on the rungs of a ladder if you're climbing up the ladder, and if you step in between, you're going to fall back down to the previous rung. So, because only specific energy levels exist, only specific energies can be produced. So if we look at electrons falling specific energies, one that might only fall one energy level is only going to give off a little bit of energy. That would correspond to red light. One that might fall two energy levels is going to give off a little more energy, so that might correspond to green light, and so on and so forth. The farther an electron falls, the more energy it's going to release. And so it's going to release a photon in the more energetic part of the spectrum. So what we saw in class when we looked through the spectroscopes and the hydrogen light was we were observing actual electrons falling back down to lower energy levels and releasing a specific amount of energy relating to a specific wavelength. Now, Bohr's model of the atom wasn't completely right. It worked for hydrogen, but hydrogen's the only element that his model worked for. And as we're going to find out, they're more like bees around a hive than in specific orbits. And that's the quantum model of the atom, which we're going to talk about next.